Hello and welcome to another episode of Naturally Curious. My name is Clayton Law and my guest today is computer science professor Richard Hurley. How are you doing today?
I'm doing well, Clayton. Thanks for having me on.
From my own personal experience, I think that when high school students don't know what they want to study, they study either business, psychology, or computer science. Were you like that when you decided to do computer science?
Well, actually, Clayton, I started out in pre-med.
Oh.
So we're going way back. So we're talking 1980. Computer science at that point in time was really for professionals. It wasn't something you would pick up in high school. You didn't have any experience with technology. My first time I ever touched a computer was a Commodore PET, and that was in grade 12 in 1979. So I didn't have a lot of kind of exposure to technology at that point. Like, technology didn't really exist relative to what we have today.
Mm-hmm.
I mean, I can remember back when a 4-function calculator would cost $100.
Oh.
Like, that's if you had a calculator in high school, you were rich.
And that is like cutting edge technology.
That was cutting edge technology in those days. So when I was doing my courses, I was doing physics and science, chemistry and biology. I had one elective and my math, so I took computer science, and I found it really interesting. I found the logic associated really interesting, so I decided to take a few more courses the following year, and then all of a sudden I was hooked. Oh. So no, I didn't start out with computer science. It just happened organically from taking elective courses.
So like from like almost second years or so, you're like, oh, this pre-med thing is overrated. Let me join this computer science thing.
I didn't like biology very much. I did well in it. I didn't like biology. I found myself very squeamish. My father was a doctor, so that's kind of thought that path might make sense to me. So I just kind of, I kept with some science courses, and I did some engineering courses, but I took a lot more computer science courses, math courses, so I ended up kind of graduating with a joint major in computer science and math.
Well, I guess it's kind of good that you realize you're a bit squeamish with blood or something in
sure
second year.
Well, it really was. It really was. It just wasn't my idea of fun at that time.
But at what point did you think like, oh, maybe I can be a computer scientist? Like, because so many people graduate maybe doing math, they're not necessarily thinking about being a mathematician like that, right? At what point do you think, hey, maybe I can be a computer scientist and maybe even become a computer science professor?
Again, that just happened after I completed 4 years of university. I was kind of decide what was going to happen next. I had some summer experiences, but nothing too terribly exciting, and not really wanting to go into the workforce. I just started applying to graduate schools like some of my other friends did, and we were kind of at the top of our class. And I got an offer from Waterloo to go directly from my bachelor's into a PhD program. Well, this sounds interesting, so I went off and did it without really thinking about what I wanted to do next.
Was it common to go from a bachelor straight into a PhD?
That was the first time Waterloo had done it, and they'd made the offer to 4 people at that point, and myself, a colleague of mine at UMB. I went to the University of New Brunswick. And there was a couple other people from Ontario, and we all did finish our doctorates and without doing our masters. But I think in hindsight, it's probably something I wouldn't recommend, because you're going from undergraduate into an area where you're doing pretty heavy duty research, and then the writing of the thesis at the very end is pretty laborious. You're producing a document which is about 300 pages, which involves your research and your results. Then you have to get up in front of people and then defend your work. So it was, again, had I known more about it before I started, I probably would have done the master's degree first, get my feet wet with research, and then decided. But it all kind of worked out.
Well, great.
Yeah, it did. Yeah.
So by the time you finish your PhD, did you go like, oh well, I'm here now, I might as well stay in a university environment and do university work, like stay in academia?
As you get closer, because this is a 5 or 6 year process. So as you're getting close to the completion, you're then thinking about, what do I want to do next? And I liked academia, but I didn't restrict my search to academia. I applied to a few companies, and this was like 1990-ish. So technology was starting to come along. people started actually having microcomputers, workstations on their desks. So I applied to different places, and I also applied to a few academic places as well. I interviewed at several academic. I got a few offers, but I liked Peterborough. I liked Trent, having come from the University of Waterloo, which was extremely competitive. The education I got there was top notch. I can't complain about that. But I found the environment too high stress.
Hardcore.
Yeah, very, very, very much. And also, I come from Fredericton, New Brunswick, which is a university town. It has UMB in it. Very small city. Peterborough is very much the same. So I kind of fell in love with the city and fell in love with the university. And I saw that at Trent, I had the opportunity to create something here. I was the first computer scientist hired into the program. This is 1991. And at that point in time, we were only a joint major. We didn't have a single major. So I saw this as an opportunity to build something of substance here. And so we've gone from a very small little program that had 3 people in their 4th year to a program now that offers majors, joint majors, several specializations, and we have 330 students, 330 majors. So yeah, I really enjoyed building what we have here, and now I'm looking at retirement.
And that's the work of 20 something years.
Yeah, that's my over 30 years I've been here. That's kind of what we've been able to do, and I've had some wonderful people to work with. I mean, I really can't take the credit here. I worked with some amazing people, and I think being part of all the process of hiring those people, because I'm kind of the senior person here now, I think we put together a really great team here that's really top notch.
Okay, so let's talk about computer science now.
Please, sure.
To me, it really feels like computer is magic. Because at the end of the day, it's just a bunch of ones and zeros doing addition. So can I say that, can I make a comparison as if I have a massive warehouse full of kids who are just doing simple addition, can they produce what we see in a computer? Is that like a fair comparison?
I don't think so. It's like looking at a bridge and realizing it's just a bunch of nuts and bolts and iron beams. It's when you put it all together, does it become a functional bridge? So the engineering process that goes into that makes it interesting. The same thing is true with computer science. Although all information, yes, can be reduced to ones and zeros, it's all the different things that work together to produce what you see on your screen. So it's a lot of hard work that has come up with it. A lot of engineering, a lot of math, a lot of computer science has put together what we see on the screen. It wasn't done overnight, as you know. If you go back to, computers were really first invented to help us drop bombs more efficiently on people. Prior in World War I, you hired a lot of mathematicians who computed ballistics tables to figure out what angles they were to lob bombs. Well, they realized, can we automate this process? And that's kind of how computers, the Second World War, leading up to it and after it, was the big area developing in what we see as a computer today. And it really was done to make their job more efficient. I'm sure we've all seen the Alan Turing movie that was on already.
Imitation Game.
Yeah, exactly. It's really about cracking, really trying to take math and automate math.
Yeah, and the magical part is really like, how do you go from ones and zero to what we see today, right? And of course, we don't have the time to go into everything about it. But say, because it is truly that at the end of the day, is everything reduced down. You see on a computer is reduced down to ones and zero, and that's the machine code, right?
Right. That's how information is stored, and really, we've chosen ones and zeros because that's the state of nature. Mm-hmm. Magnets are either positive or negative. Light switches are on or off. You have a high or low electrical capacitance. That's why we've chosen binary, because it fits nicely into nature. So the things that we work with, the things that we store information on, absence or presence of pit on a DVD. These are really kind of what we're looking at. So yeah, we've chosen binary for a reason, not just because we want to complicate students' lives. It's because that's what exists in nature.
So, high-level code, high-level language compared to low-level languages. Mm-hmm. Low-level language is closer to machine code than higher-level language, right?
Yeah.
And in general, lower-level language is harder to use for human being, and higher language higher level is easier for human to actually read it.
Yeah, if the language is designed properly, a typical third generation language like Java or Python or Fortran, when you read the statements kind of left to right, top to bottom, it
like
actually
English.
reads in English.
Yeah.
It's really bad English, but a programming language is really nothing different than a spoken language like English. There's nouns, there's verbs, there's punctuation marks. I mean, the really neat thing about a programming language is, unlike a spoken language, the dictionary for a programming language consists of about 75 words. So it's not like, so if I know one language, learning another language is trivial because I just have to relearn the words, 75 of them, and kind of figure out the grammar, the punctuation that goes into it.
So why would anybody learn? Like, what is the point of a low level language nowadays? Because higher level language just gonna turn into machine code anyway,
Yeah.
and it's easier to read. Is there a reason for people to use low level language?
It's like, let me give you a comparison. It's like we know that our calculator or our phones will add, subtract, multiply, and divide. Is that a reason why we shouldn't learn how to do that ourselves? So if you just relied on your phone to do your math for you and not be able to break it down and do it on pencil paper, do you think you're better off? The answer should be no.
Yes, the answer should be no, but I'm thinking like, will it be? Like, do I really need to know how to do long division?
Well, again, it's a matter of knowing, understanding things in their first principles.
Right.
The idea with why we should learn a low-level language like assembler is that code is still being written in assembler. When you take a high-level language like a third-generation language, it's being converted and converted and converted down till you get to a point where it's machine code. Each place along there's inefficiencies being added to it. So a high-level language like I said, Python isn't the most efficient to run. So if you're designing a real-time operating system, something, for example, that would monitor the amount of water in a nuclear reactor, you want it to be able to react quickly. High-level languages don't have that ability. Whereas if you've written the code in assembler, you have the ability to control exactly where information, you're controlling information as it comes into and out of memory, into the different CPU registers. High-level languages relies on the software, that the compilers, to do that for them. So you don't have the same control over it as you would over a low-level language like assembler.
So it's almost like high-level languages, you need more translator. It's like, oh, this person can speak like Chinese and English, and then this person can speak English and Spanish, and then the more interpreter, the more translator in the middle is worse because it's less efficient, and that is like the big advantage of using a low-level language. Would you say?
It's really about having the control. A lot of research is going into what are called optimizing compilers. A compiler that will take a program and convert it into the best form possible. But again, you're relying on the software to do that for you. I mean, software is really bright. There's no issues that the software is not going to do a good job. But again, you don't have the same control as you would if you're writing the program yourself at a lower level, like assembler. So yeah, assembler is still part of every computer science curriculum in North America and probably Europe. It's that integral. It's really important to know how to add, subtract, multiply, and divide before you start using a calculator. So before you start using high-level languages, it's really important to have a look at. When I was going to university, I had 3 courses in assembler because there wasn't that many high-level language. But nowadays,
was assembler like a high-level language?
No, actually it wasn't. We did Fortran, and we had COBOL, we had C. I mean, C was written in 1970. C, you're familiar with the C language, yeah? Do you know why C was developed? Let me give you a history link. There was a couple of guys, Brian Kerrigan, Dennis Ritchie. These were a couple of long-haired dudes that worked at AT&T Bell Labs, and they had a PDP-11, which is a mini computer, and they were playing a space game on it. Now, this space game didn't work very well, so they decided, hey, let's design an operating system that will allow our game to run better. So they designed Unix. Mm-hmm. In the process of designing Unix, they didn't like the languages that were out there now because they didn't want to work directly in machine code. So they created C to write Unix in so they could play their game better. So C has been around since the 1970s.
like, I mean, I don't really know, but C is such an influential language,
is.
and it's like you can't. It's just, to me, just like, hey, there must be something very, very, very special about C, that everything else in the 1970s died, but C lives on.
Well, C is a language which is it's because of its design and its purpose. It was intended to be able to write operating system code in it. You know, you're talking about something that works with your printers, with all your device. I mean, that kind of level. C is a language that actually kind of sits between high level and low level. That is, within a C program, you can actually have code that you can start manipulating bits. No other language provides that at that level. So because it has that ability to work at the low level and the high level, it became very popular for things like operating systems, games, graphics, that sort of thing. So it became very popular. And it's not going to go away.
Like, is it fair to say, like, it's not the best low-level language,
No.
it's not the best high-level language, but it's very flexible.
It does very well, yeah. And then they added C++, which is you took C and you added object-oriented programming to it. And a very bright person once said, C, when you use C, you can actually shoot yourself in the foot. When you use C++, you can blow your leg off. Because it's a language that assumes you know what you're doing. So if you want to write into the middle of your operating system, it assumes you want to do that. And you know what you're doing. It allows you to happen. You can actually write a C program that overwrites itself.
What?
Yeah, a program that changes its own code as it's running.
Oh, okay.
Yeah, because you can write anywhere you want in memory. So if you know where your program is in memory, you can overwrite.
No.
So yeah, I mean, it's a great language if you know how to use it.
Yeah. I read something from somewhere, I don't know, but it says something like HTML works even if you have no idea what you're doing.
Yep.
It just works.
Yep.
And I feel that when I do it at work, it's just like, I don't know how to code for real, but I can just do a lot of like guesswork, and it just works.
A lot of the markup languages, all you need is an example of how it works, and you can simply either change the body of that, or I mean, you can use it as a starting point to create your own web page, for example. Yeah,
just hit Control C, Control V, and half of the work is done.
Exactly. Whereas, I mean, you can actually get the drag and drop systems that will write the HTML for you.
Yeah.
But it's a markup language. It's not that difficult. When you go to XML, it becomes a bit more interesting. But no, you can't do that with C. In fact, there's a competition someplace in the States where you get money for writing the most cryptic program. That is, you look at it and you can't possibly read it because, again, there's so many different really neat things you can do in C that when you look at it, it just looks like a bunch of strings. Because you can write programs.
Is that like a real competition, a joke competition?
No, it's a real competition. Yeah,
Oh,
yeah.
cool.
They give you a theme, and then you write the most cryptic C program to do it.
Oh, cool. I'm greatly amazed by the people in real life who can speak multiple languages fluently.
Yeah, I am too.
And I feel like for most people, like, they can't really truly be fluent in more than 2 languages. And like you said earlier, in the world of computer science, programming dictionary only got 75 words. So is it truly possible for programmers to be fluent in multiple languages?
Oh, easily.
Okay. And I shouldn't be too greatly amazed when people, they can do multiple languages.
And the thing about programming languages, once you know one really well, it's not that difficult to pick up another one because all programming languages have arrays, they have loops, they have if statements. It's just a matter of determining how this happens in another language. Now, if you take something that's like a completely different paradigm, like R versus C, there's nothing same. R is written to do data manipulation, C is written to do systems programming. There's not a lot in common. Whereas Python and C, for example, a lot of overlap between them.
Yeah, I'm learning C. I learned C# and I'm learning R, and it's just like they are so different. And this is why I have this idea of like, hey, is it truly amazing when people say, oh, I'm fluent in both C and R?
No, R is a different thing, for sure. And then there's APL, programming language. Again, it's been around for many years, but with very simple commands, you can have it multiply matrices. It was designed as a math companion, developed in the 1970s by a guy in Toronto, by the way. He's still around. Yeah. And it's still very popular. But engineers use APL a lot.
There's another like cool things that I find about computer science is that when you talk about this math thing was discovered by Gauss, who's dead for like a couple hundred years now, and but in computer science you can still hear like this very influential thing was developed by a guy in 1970 and he's still around.
Yeah, absolutely.
Like and that is
we're a really new science,
and that's very exciting.
I mean, if we go back in history, you talk about people like Charles Babbage, who designed analytical indifference engines, but they were kind of the forerunners. They had all the same input-output processing that computers do have today, but they just didn't have the technology, the hardware to be able to create these. I mean, the first programmers were barbers.
Pardon me?
The first programmers were barbers.
Oh.
A programmer is somebody that executes after the French Revolution. And all the rich aristocracy lost their heads. There was no need for barbers.
Oh.
So the first computers were people who were hired because since there was no people with long hair that needed the haircut, they were hired to compute tax tables. So they were the first computers doing computing. And then it kind of progressed from there. Yeah, there's a lot of really interesting history, but our real history started during World War II. Like that's when the main crux, Turing and all the different work, Aiken, all the different work on creating these machines to do really, really quick math. And then obviously after that, they saw these things had a use, and so business wanted a piece. So, they started creating COBOL and machines to do business processing like IBM, and it just kind of snowballed. Then everybody wanted, the individual public wanted, so microcomputers came along, and then
general purpose.
Yeah, absolutely, yeah. Then it all started, but military, then business, universities, and then
general purpose.
Everybody gets them. Yeah.
In high school, I did like application math problems using quadratic formula, and then I don't know, for something like you're shooting arrow from a rooftop and then calculate where is it going to land or something like that. And then when the quadratic formula spits out two answers, we'll just say, well, we ignore the negative ones because it doesn't make sense to have negative distance. And but like if you and then it makes sense for a human, but for a computer it will say something like, it will land in 25 meters and negative 20 meters, and that's kind of like opposite of what human does, right? Like because for human it just be like, we'll take the 25 meters because negative 20 meters doesn't make sense. That is something that computer scientists have to take into account. Obviously, the example I had was a very trivial one.
Yeah.
And I see a lot of things like these in like communication between computers, like the two generals problem, where it's like, well, it's really trivial in real life how two generals can communicate with each other, but in the world of magical computer science land, that is something that computer science needs to worry about. And did you find that really challenging at the beginning when you have to try to think like how a computer would think?
I don't think so, Clayton. I think because you're not thrown a very difficult problem at the start. They kind of build these things on you kind of build up your repertoire of complex problems. You start with simple ones and you go slightly more complicated, and then as you move on upper year courses, you work at more and more complicated kinds of problems. So you're building up your own database of understanding of how these things work.
You're building up some sort of like an intuition, and just
absolutely.
Like, this just works because I know, like that kind of.
Not everybody can be a computer scientist. Not everybody can be a musician. Right. I mean, I certainly nobody's going to hire me to sing because I don't have that part of my brain doesn't fire off properly. So the way you think about a problem really lends itself towards a programming type of solution. So people who think logically, mathematically logically, tend to do better. Engineers tend to make really good computer scientists. They're expected to attack a problem by looking at it from a global view and then kind of honing in on, and that's exactly how we deal with large programs. But you learn that over time. So no, I don't think it was magic. It's just really more experience. I mean, a doctor you don't just throw them in the middle of an operating room working on a heart. You build them towards that. You have to learn. It's all about learning. Yeah.
You were just saying like, oh, what kind of people would be good at programming? What do you think of philosophers? Like, because philosophy has a lot of logics in it.
Sure
as well.
It does, and I absolutely some of the best computer scientists I think came through the area of philosophy because again it's the way you're thinking about a problem. Yeah, I think yeah.
Because I read it somewhere somewhere. It says something like law school admission test are very like 3 groups of students are very good at law school admission test. One is the first type is philosopher, and then the second and third types are mathematician, like math student and computer science student, because it's all about logic and it's like on the surface it really doesn't seem like philosophy and computer science has much in common, but
we have 3 courses with philosophy.
Oh,
yeah,
I actually know that.
Yeah, symbolic logic, cyber ethics.
Yeah,
there are a lot, and yeah, I mean, part of a computer science curriculum would be to do courses in logic as well, and it's the basic kind of logic. There exist and for all kinds of quantifiers associated with symbolic logic. So yeah, I mean, all students in computer science take one, and then that's a really big part of what's being done in philosophy. How you win an argument, you put together your appropriate statements, you kind of crap them all together, and then hopefully what you end up is true when you're done.
This is why the thing in the program is called an argument. Oh my god, I just made that connection.
Yeah.
Do you think that thinking about these things, like, oh, how would a computer think, is good for like university preparation for high schoolers?
I'm not sure how to answer that. I am really pleased that they are requiring kids as early as elementary school to get some experience with coding. I mean, a lot of kids that come into university still nowadays had very little exposure. They realize that this is obviously an area that there is employment at the end of the tunnel. So they do come into it thinking that I'm going to get a job, but not really knowing what they're getting into. So although we don't have a huge dropout rate, it's probably is higher than, say, psychology in their first year. They don't drop out, they just change majors.
Right.
And I think by having students in elementary school getting some exposure, they at least understand what they're getting into when they come to university.
Yeah, and I also think that it's very important for them to know, because you don't want to get cheated on by companies.
Absolutely.
Because when you're talking about programming, it's not just about programming.
No.
You're also talking about like cybersecurity and all that. And I think it's like, I mean, it's the 21st century, and it's very important for people to know that, I guess. Yeah.
Well, computer science is not just programming, as you know. It's a very small part of what we do. In fact, most university-trained computer scientists don't write code. They design code. They design problems. They come up with solutions, that kind of thing. No, it's important to know how to code. But yeah, most of them don't really get directly involved with it after some period of time. They end up, but yeah, it's something I think everybody should have some exposure to.
Would you say computer science in general requires a lot of creative work? Like, it's very creativity driven?
Absolutely. I mean, if you're going to design a new interface for somebody, then you have to have that kind of thought process to where do you put the icons, what colors you're going to use. That is important. Another thing that I think is a real misnomer about computer science is that you don't need to have good English, or you don't need to be able to write. In fact, there's a lot of writing that goes on in what we do. Even you're talking about user documentation, but anytime you're doing presentations, we do a lot of that. You're interacting with the public an awful lot.
Yeah.
So yeah, there's a lot of humanities skills necessary. The interpersonal skills are really big and really important for today's computer scientist or software engineer.
Can you give me an example where this Picasso's quote holds? Learn the rules like a pro so you can bend the rule like an artist for computer science.
No, I can't.
Yeah, it's a bit challenging to think of it.
Had you given me that information beforehand, I might have had a chance to think of it. I mean, there's always nefarious people out there that might want to be able to bend the rules, so you create software with a trap door, right? So although the company has your software, you can always get into it if you wanted to. I mean, that exists. I mean, there's a real ethics component. Like engineers have to have their ethics when they're building. Computer scientists also have to have their ethics. I mean, any good computer science student has to have done a course in ethics.
Right. Yeah.
You know, what's right and wrong. Because it's, again, if you're designing software to provide security for a banking system, then it's really important that your company builds that software with those ethics in mind. Yes, I mean, it's no different than putting up a fence and keeping a key for the door.
Yeah, I think like again, it's kind of difficult to think of it off the top of your head, but it's like rules, as in not like legal rules, but like computer science rules that things that you just shouldn't do because your professor says so. But like, in this moment, if you bend the rules slightly a bit, it actually makes things more efficient. Like,
well, you've heard of white hats and black hats and gray hats. Yeah, I mean, white hat is supposedly somebody whose job is to help you find the security issues with your software. The black hat is obviously looking for them, but they're looking for them from a more mischievous position. And the gray hats, you really don't know which way they're going to go. But yeah, just because you have the ability to do something doesn't mean you should. Right. Just because you have the ability to enter that store doesn't mean you should. Just because you have the ability to go on to the White House computer doesn't mean you should.
Right. What is your favorite programming language?
Mine is C.
Why?
That was probably my first, when I started my PhD, I didn't really have any exposure to C as an undergraduate student. But when I started my doctorate, the first course I took, course in modeling and simulation, they wanted me to use C. And I fell in love with it. I realized I could do so many neat things with it that I couldn't do with Fortran or COBOL, or we were kind of big on PL1 at UMB. PL1's a kind of combination of Fortran and COBOL developed by IBM. But yeah, it's really more from my first language I loved. And I use it. That's the language I program in still today. I know how to program in R and Python, but I still go back to C because I find I have more control over what I'm doing.
This is a question that I asked to all of my guests. What are you up to now in terms of teaching and research?
I'm on sabbatical.
Yep.
So I've had, since my last sabbatical, I've had 6 or 7 graduate students complete. So I'm just taking that information and trying to write some publications with it. I was involved in a big research problem last year where we're analyzing student data of students that came to Trent through college to university transfer agreements. So I've just completed a paper on that, and I'm hopefully going to go to UBC to present it.
All right, Richard, thank you for joining me today.
Well, thank you, Clayton. Good luck.
It was a pleasure talking to you.
Oh, thank you.
You can find the show notes of this episode on anchor.fm/naturally-curious. And until next time, stay curious.